So now I'm demoing GIPC, and in this part we're going to see the remote method calls being invoked on a client or a not inputting client by an inputting client. So as you can see here, we're proposing a command to the server, and the command we're proposing is to move 100, 0. So as you can see here, the simulation has already returned after it's made the call to the server. So now we're in the server, and we're going to step through and see how the server calls each client callback with the command that was passed to it. So as we step over, we'll see that each client callback is called execute command, and the server doesn't block waiting for a response from these. It just goes through and calls execute command for each callback, and then continues its functioning. So now that we've resumed, we can see that the server is no longer blocked, waiting for a response from anyone. So now if we step back to one of the clients, we'll see that execute command has been called, and it's called client.execute command. You see it's move 100, 0 again. So if we resume, we'll see that each client, after execute command has been called, resumes its normal functioning. And you can see here that the command processor has passed the command that we received. And finally, so we've shown two client set of execute commands. We'll show the third one. And you can see that the first two have moved and the third is not so far. So once we click resume here, we'll see that this client moves as well. Yep, and you can see all three clients have moved forward. So next we're going to show each client, or two clients rather, changing their broadcast mode and show that commands entered while their states are null, while we're waiting for a consensus, are ignored, and then finally that each client successfully will update its broadcast mode after reaching consensus. So now what we've done is we've entered atomic false for client 1 and client 2, and as you can see they're both blocked on the set atomic call. So if we resume them, you can see that in the call stack there is a GIPC client callback for a proposed atomic broadcast, and now that the new value for atomic is going to be set to null. And that's because once we've received a server asking if we can update our value, we set our value to null to indicate that we're going through a consensus process. So as you can see, the new value for both client 1 and 2 has been set to null. And that's because the server has asked them if they can update their values, and they both return true. And while they're waiting for consensus among all the clients, they're going to set their atomic values to null. And each client is going to do this. As you can see, we step through client 1, and client 2, and client 3. Now we're in client 3, and we see that a new value with a Boolean value has been sent to it. And that's because we've reached a consensus, everyone said they could change it, and now our server is asking us to change it to the new value. So now we're going to enter two commands, smove 100, 0, and move 100, 100 in client 1 and client 2, the ones that proposed atomic false. And what we should see is that both those commands are ignored because we have a null atomic broadcast value right now. Now we're going to step over and resume, and you can see that we're now in our client sender, and you can see if the client is waiting for atomic, we just print out command ignored, and we return. So for client 1, we ignored the command that's passed in, and for client 2, we should see the same thing. So client 1 and client 2 ignored both those commands because they're in the process of updating their atomic broadcast value. So now you can see that our callbacks are receiving a false value for atomic because that's what we asked to change. And if we step through, you see each one has changed it. And now we're going through and executing the second call, the broadcast from client 2, to change the atomic broadcast to false. And we're going to have to go through these steps again because we had two proposals made, one from client 1, which was already executed, and now we're stepping through and executing the proposal from client 2, changing atomic to false, which shouldn't change anything because each client was already set to false. However, we still need to go through the steps of making a proposal, setting our values to null while we wait for consensus, and then finally updating the values back to false once we've reached a consensus. Finally, we're going to show that now we can execute one command in an inputting client and see it executed into non-inputting clients. So you can see here for client launcher 1, we're executing move 100, 0, and you can see the proposal is proposing the command to the server, and the server is calling execute command in each client. And you can see at the bottom, a receive call invoker has received a command for move 100, 100, and now we're in client 2, and it's also received that command. And if you look at each client, they've all moved forward by 100, 0. So let's go to another client now and try and execute another command. And we're executing a move back negative 100, 0. So we should see that each client moves back to where they started. As you can see, we're following through and execute command in each client, and each client blocks in the execute command call, which is invoked by the server in their callback. So as we progress through and go through all the breakpoints for each client, when we go back to the simulation, we should see that each client is back where they started. And that's true. Each one is at the path they started on. So in this section, we're going to be running the tests. And the first ones that are shown are just being run locally, and it's going through and running the test for each IPC mechanism, NIO, RMI, gypsy, and then also running it for local is done initially, and it's the same for each. And as you can see here, we are doing running it for each mechanism. For each one, we're doing atomic and non-atomic. Now, the results are shown here, and as you can see, the local is the same for each. For NIO, atomic was faster than non-atomic, and that's because non-atomic interleaves the update of the um, graphical interface with the sending of commands, whereas atomic simply sends the commands before probably having to update. RMI, as you can see, was much faster in atomic than it was for non-atomic. And again, that's probably because for atomic, we're just timing how long it takes to send the commands, whereas for non-atomic, we're timing the amount of time to both update the graphical interface and send commands. Finally, for gypsy, we see that the atomic was 3 seconds and much faster in non-atomic than for RMI. And that's probably because with gypsy, instead of where RMI we have synchronous method invocation and we wait for the server to respond before going on to the next thing, with gypsy, we're able to have asynchronous method invocation, and that allows us to run non-atomic much faster than in RMI. For Cybers, I was able to run my NIO tests, but when binding my ports for gypsy and RMI, I had some errors that I couldn't overcome. And so the results that I got from this were that the NIO ran much faster here than on my local computer, and that's probably because there was no GUI here, so it was running headless. And as you can see, atomic true took longer than atomic false. And that's probably because in this case, since there was no GUI to update, atomic false is really just timing the amount of time it takes to execute these commands, probably interleaved with a bit of sending, where atomic true was probably having to deal with some sending, receiving, and executing, which might have added a bit of the time. As you can see, it's a very small difference, 0.2 seconds.